All right, so yesterday we talked about reaction kinetics, and we said that just because a reaction is spontaneous, it doesn't mean that a reaction will occur quickly. We need to know about the reaction rate. And we said that the rate equation always has a rate constant multiplied by the concentration of some of our reagents in our reaction mixture. And we said that the reason that concentration matters is when we increase the concentration, we increase the probability of molecules bumping into one another. Therefore, we increase the probability of a reaction occurring, right? We said we can also go through and experimentally determine the order of a reaction, the rate order. So in this one, I gave you an example where in order to find the rate order, we changed the concentration of each of our reagents independently and saw what effect that had on the reaction rate. Somebody asked me in office hours, how do we know about the rate of the reaction? If you go on and take analytical chemistry, there's actually experimental techniques where you can basically determine how quickly your products are being made in a reaction. There's a variety of techniques for doing that. So in this example, we saw that doubling the effect of our sulfur reagent had no effect, but doubling the effect on our reagent with iodine doubled the rate. That means we can determine the rate equation, and we said that this must be a first order reaction. This is often what chemists do when they're experimentally studying a new mechanism. So we'll talk about reaction mechanisms more next chapter. All right, what else were we kind of neglecting though this whole time? We've been talking about concentration a lot. What's the other part of a rate equation that we're ignoring? Rate constants, right? So let's finish up today talking about that. So what about little k, the rate constant? It's actually pretty important. It often gets neglected because it's just treated as a constant. It's not an experimental variable oftentimes. But a lot of things can impact k. Number one is temperature. All right, if we increase the temperature, are we going to increase or decrease the rate of molecular collisions between different molecules? Increase. So it increases the rate of collisions. And then a cool rule of thumb is that for every 10 degrees Celsius increase in temperature, you will double your reaction rate. It's actually pretty dang close to the truth, but we can go in and experimentally determine this in labs too. So what happens if we increase the temperature by 20 degrees Celsius? We quadruple the rate. So there does become a practical limitation though. Why don't we just set every reaction to go at 5,000 degrees Celsius? What's that? You'll burn off all your stuff. Getting back to our Gibbs free energy argument, if we increase temperature high enough, we're going to drive disorder, right? If we drive disorder, it's going to want to typically turn into charcoal and CO2, right? So we have to be aware that we can increase rate, but it needs to be within reason for that reaction. All right, number two is orientation and sterics. All right, so these are kind of new terms. Does anybody know what sterics means? It's how bulky something is. So sterics is referring to the bulkiness of a molecule. A sterically large molecule is a molecule that is crowded, right? It's got a bunch of stuff hanging off of it. It's hard to access. What does orientation mean? It means, can you attack one reagent this way, that way, or any way? Is it dependent on the angle of attack? So we have to look at the angle of attack and the accessibility of the approach. So let's make a note here. This is the angle of attack and accessibility of approach. So you can almost think about it like Star Wars. You remember when Luke goes down that canyon and is trying to shoot the torpedo? It's kind of like that, right? He had to go at the right angle and he had to access it from the right way. It's the same thing with a molecule, right? The probability drops a lot if you're limiting those two factors, if you have to attack from a pretty narrow angle and it's crowded. All right. Third one is activation energy. All right, does anybody remember what activation energy means from Gen Chem? It's the energy required to initiate a reaction or to get the reaction to occur. So it's basically a measure of how hard it is to initiate a reaction. Some reactions have really, really high activation energies. Some will occur spontaneously, meaning you can just look at it wrong and it will go like that. We have to keep this in mind whenever we're studying a new reaction. All right, so some reactions have incredibly high activation energies, like prohibitively high. What do we do if we run into a reaction with a high activation energy? You can throw in a catalyst, right? So catalysts are kind of a side note here. All right. One thing I often hear students say is, well, a catalyst lowers the activation energy. It's kind of true and kind of not true. What a catalyst does is it doesn't lower the activation energy so much as it takes you on a completely different route to get from point A to point B. So it's a little bit different that way. But let's make some notes about catalysts. A catalyst is something that is not consumed. Which means, do you need very much of a catalyst for a reaction to go? No, sometimes you need a very, very small amount. It just gets recycled and reused over and over and over and over again. All right, and then like I said, it doesn't lower the reaction activation energy. It takes you through a different reaction pathway. All right, so we'll talk more about catalysts a lot in lab, but catalysts are often associated with green chemistry, right? Because it requires less energetic input to get a reaction to occur when you have a catalyst present. And because it's not consumed, we're gonna really improve our waste stream by minimizing the amount of stuff we're throwing out at the end of a reaction. Make sense? All right, so now I'm gonna give you a theoretical problem to chew on. So I didn't print this out for everybody, but you're more than welcome to kind of draw this out. It's the following reaction coordinate diagram. What I want you to imagine is right now, imagine being stuck in this intermediate well, and you have two options. You can either go over this path on the left, we'll call that reaction 1, or you can go this path on the right, we'll call that reaction 2. Does that kind of make sense? So these are two different routes we can go through to get to product 1 or product 2, depending on the direction. All right, my question for you is, how might you be able to favor the formation of product 2 over product 1? So talk about this with your neighbor and see if you can come up with an idea to try to get product 2 over product 1. All right, so let me try to give you a few hints on this one. So my first hint is between product 1 and product 2, which one is the more stable product? So between product 1 over here and product 2, which one's more stable? Product 2. So if it's more stable, that means that energetically, the system would prefer to reach product 2 than product 1, right? Okay? All right, second question is between reaction 1 and reaction 2, which reaction is easier to initialize? Reaction 1, why? It's got a lower activation energy. If we look at this activation here, that's a much, much lower hill to climb than this activation energy over here. All right, so we've got kind of competing interests at stake. On one hand, we're saying the activation energy to get to product 1 is lower, but product 1 is less stable than product 2. Does that make sense? Does anybody have an idea for how we might be able to favor product 2 over product 1? What do you think?
Just increase temperature enough to overcome EA1 and EA2.
Okay, so you're saying throw in enough energy where this intermediate has enough energy to climb over EA1 and EA2? I think that's a really good approach, right? So let's say you do that, then it has enough energy to go to product 2. What happens if some of it goes over to product 1, though? It would also have enough energy to do the reverse reaction, right? And then eventually go all the way over to the product 2 side. All right, so I want to show you a little video for how this works. And I'll leave the sound off. So you see, it's a little hard here. Let me actually shut off all the lights. It'll be like a movie. That work? Oh yeah, there you go. We'll set the mood for this reaction. All right, so on the left-hand side, you see how this barrier on the left-hand side is lower? It's got a smaller activation energy. It's a little hard to see. On this side, the barrier is higher. But on the left-hand side, the product energy is a lot less stable than the product energy over here. So it kind of mimics what we're viewing in that last graph. Make sense? All right, so what he's done is he's put beads in that intermediate, and then he's got it sitting on a speaker, and he's going to use the speaker vibration as a source of energy. So let's take a look at what happens. So let's give him a little bit more time. There we go. So you notice how some of them are going all the way over to the right. The majority, though, are going to the left. But let's see what happens over time. I'll let it go. Let it go. Let it go. Might take a little while. But now it's turning into a statistical game, right? You see how the reaction on the left is kind of in equilibrium? This side of the equilibrium is favored, but eventually some of these are accidentally getting trapped all the way over on the right-hand side. What about the reaction on the right-hand side? Is the reaction on the right-hand side really under equilibrium control anymore? No. So one reaction on the left is under equilibrium, the one on the right is under non-equilibrium. So things are starting to get trapped all the way over to the right-hand side, even though that's not what initially occurred at the beginning. It's kind of interesting. So what this is referred to as is this is referred to either as a thermodynamic trap or a thermodynamic well, meaning once you fall down that well, you cannot get out of that well anymore, right? So that's our thermodynamic product, meaning our most stable product. Things tend to get stuck there under high temperature conditions. Does that make sense? All right, so kind of a unique example showing there. No, I'll show you another one though. It'll be amazing, I promise. All right. So over here, we just saw the video. it is crank up the heat. So heat things up, you can trap the product in a thermodynamic well.
That will still work even if we crank the heat up slowly, if we force it to slow ramp up.
That's a good question. So your question's about slowly ramping up the heat. Let's see what happens when we do that now. So let's finish this part though. So heat things up, you can trap the product in the thermodynamic well, kind of like we saw in the video. Therefore, this product is referred to as our thermodynamic product. All right, now my second question was, how do you favor the formation of product 1 over product 2? Don't get it as hot, right? That would be the other option. So let's put this down. So don't get things as hot. All right, do you want to see the video for this one? Yes, because that's easier than writing notes down. All right, so same exact situation, right? So in this one, what he'll do is he'll still heat it up, meaning the speaker will turn on, but with less energy. So maybe this time, instead of having enough energy to go to the right, there will only be enough energy to go to the left. So let's see how easy that is. So you see how those beads have enough energy to overcome the lowest activation energy pathway, but not the higher activation energy pathway? And we're able to control it by only giving it enough energy to get over that little hill. But then once it's in that product 1 well on the left, it doesn't really have enough energy to go all the way back to that same intermediate anymore. So now product 1 is no longer under equilibrium control. A lot of times students will look at this and they'll say, but you still have stuff on the right-hand side, right? Is chemistry always clean and perfect?
Yes.
Not always, right? So in this case, oftentimes you do end up with a mixture of products, but in this case, we can clearly see that product 1 is being favored over the product 2 on the right-hand side. So this is a nice visual demonstration of the statistics going on here. Yep.
Can we have like equilibrium between product 1 and intermediate without having product 2?
So the question was, can you have an equilibrium between product 1 and product 2 without an intermediate?
Without having product 2.
So can you have an equilibrium?
So from intermediate to product 1 and without intermediate without having product 2.
So you could have an equilibrium between product 1 and the intermediate, assuming the delta G value wasn't too large, right? So do you remember in the lecture the other day when I said, kind of down here, if delta G gets larger than -20, meaning more negative, then the reaction is essentially under non-equilibrium conditions, meaning the reaction won't proceed in the opposite direction anymore. So we have to know the value of delta G before we can really make that claim. Good questions, though. All right, so let's kind of fill in some of these terms. And I've got the links down here in case you want to watch this at home on your free time. Friday night movie night. So the thermodynamic product is your most stable potential product. Right, we said once you get into that most stable well, you're not going to get out of that well because the reverse reaction has an activation energy that is simply way too high. Your kinetic product is going to be different. Your kinetic product isn't going to be your most stable product necessarily, right? What do we look at with our kinetic product? The lowest activation energy. So it's your pathway All right, the tricky thing is that sometimes your thermodynamic product is also your kinetic product. We need to know about the activation energy and delta G before we can really make the claim as to which pathway is going to be favored, the thermodynamic or the kinetic. Does that make sense? So they're really looking at two different things. All right, so now what we need to do is something kind of related to what we saw up here. This was a one-step reaction where we were in an intermediate and we could go through reaction 1 on the left, reaction 2 on the right, implying that the intermediate is midway through a reaction that goes through more than one step, right? So let's make some reaction coordinate diagrams showing multi-step reactions. What I mean by a multi-step reaction is, let's say we have A going to B in one reaction, and then B goes to C in another reaction. Sorry, I should turn the lights back up, huh? There we go. So this is a multi-step reaction. We can draw our reaction coordinate diagram like this, where we've got our potential energy, or Gibbs free energy over here, and we've got our reaction progress over here. All right, so let's say I've got starting material A right here at some potential energy. All right, let's say I've got B at some new potential energy, and then C will be down at this new potential energy here. So they're all at different potential energies, right? All right, do you think the process of A going to C will be spontaneous? I would say so, right? Because if we draw a horizontal line out here, we're going to have a net drop in energy going from A to C, meaning this reaction should be spontaneous. Will delta G be positive or negative? It'll be a negative delta G for this reaction. All right, so now we can go ahead and we can start to connect this. My question for you is, do we just connect this with a straight line? No, it has to have a unique activation energy, right? Meaning that there must be a hump between A and B. So what we'll do is we'll do a hump like that. And what I want us to do is to identify the activation energy for this reaction. All right, so my question for you is, the activation energy what I'm showing with the black line, or is it what I'm showing with the red line? Check with your neighbor and see if you agree about the activation energy. All right, how many of you think it's the black line? All right, perfect. So when we're looking at activation energies, we're looking at the hill we have to climb, right? So what I'll do is I'll call this one EA for activation energy, and then I'll put a little subscript 1 for saying that's the first step of this reaction pathway sequence. Oftentimes, we include this little double dagger at the top of the hill. This is called our transition state. What do you think's happening in a transition state? It's changing from one molecule to another. What do you think is happening to the bonds during that time? They're being broken or made, for that matter, right? Are they truly broken or made? No, they're kind of halfway in between, right? So it's the energy level where bonds are being both made and or broken at that same time. So that's a transition state. All right, once we get to B right here, are we still kind of in between making and breaking bonds? No, it's a true intermediate. The bonds have already been made and broken, but it's just kind of resting there. All right, so B would be an intermediate. All right, and then B going to C, we can say, all right, let's do, actually, I'm going to slide this over. B will go to C next, like this, and then land there. The activation energy for this one is going to be like that, right? So over here, we can call this our EA2. And again, it will have a double dagger, and this will be our second transition state. Does that make sense? All right, so my question for you is, what's the rate limiting step? Is the rate limiting step going from A to B or B to C? And why? Check with your neighbor and see if you agree. All right, so let's see a show of hands. Who thinks A to B is rate limiting? All right, that's good. It looks like most of the hands. Does anybody want to share why they think A to B is rate limiting? What do you think, Anthony? Has the highest activation energy. So up here, we'd say A to B. And it has the highest activation energy. Meaning the pathway from A to B, you must have had enough energy to overcome that hill. If you have enough energy to overcome EA1, you definitely have enough energy to overcome EA2, right? So EA2 is not a problem. The problem is just getting over EA1. Does that make sense? All right. So this is how we tend to show multi-step reactions. Let's do another one. This is going to be practice. So that's a good question. So the question was, would the B to C step be spontaneous for this? Yes, it's still a downhill reaction, therefore it would be spontaneous. Would the net reaction be spontaneous from A to C? Yes. From A to C, it would still be spontaneous because C is more stable than A. What about A to B? It wouldn't necessarily be a spontaneous reaction, but just like we saw in that video, statistically, some of our beads can make it from A to B, and then once they get stuck in B, they're going to quickly make it over to C, and then quickly we're going to trap things all the way over in C. Does that kind of make sense? It's really hard when you read this in a textbook. It's why I like that video, is it shows that statistical game that we're playing, that even a non-spontaneous reaction, despite it being non-spontaneous, going another direction, it can get you to a product that's stuck in a thermodynamic well. It's a good question. All right, so let's consider this reaction. I'm just going to give you this, and I'll say, all right. My question for you is the number of intermediates. And yours better be as pretty as mine, because I spent a lot of time on this. All right, if you got that, then the number of reactions in the multi-step sequence. All right, so let's see a show. Show me with your fingers how many intermediates you think there are for this one. All right, so I'm seeing mostly twos. How do we know that there's two intermediates?
Between
Yeah, because there's two values in here, right? So we've got a value here and a value here. Those must be intermediates. So it must be two intermediates for this process. All right, how many reactions for this multi-step sequence? So what I would say is this would be one reaction, right? This would be a second reaction. And then this would be a third reaction. So I'd say this would be 3 total reactions. So just by seeing the reaction coordinate diagram, we can make some simple assumptions about the number of steps required for a reaction to proceed. All right, let's do one last thing before we head out today. Do the Hammond postulate. All right, the Hammond postulate is a little bit weird when you first write it out, but I'll show you what it means. It means that a transition state will more closely resemble the starting material, I'll just abbreviate starting material SM, intermediate, or product that is closest in energy. All right, what's occurring in a transition state again? A transition state is the energetic level where a bond's halfway between being made or broken, right? Can we isolate a transition state? Like, can I get a transition state and put it in a bottle? No, you can't isolate something where a bond's halfway between being made and broken, right? Can you isolate an intermediate? Yeah, definitely. Can you isolate a product? Yeah. Can you isolate a starting material? Yeah. So you can isolate all 3 of these things, but you can't isolate the transition state. So we have to kind of imagine what a transition state looks like by using the Hammond postulate. So let's take an example here. And this is an example we'll see next chapter. But in this reaction, the first step is that iodine will actually just fall off, just all on its own, randomly. All right, when it does that, that means that iodine will now have a negative charge and be iodide. What else am I missing, though? Positive charge on the carbon, right? All right, so now the question is, well, what the heck does the transition state look like in this process? So let's first draw a reaction coordinate diagram for this process. We know it's a one-step reaction, so I'll just put energy over here, reaction progress down here. We know it's a one-step progress, or one-step reaction, so it must only have one hump in the reaction coordinate diagram. All right, my question for you is I'm going to label this A over here as starting material and B over here. Which one do you think is more stable, A or B? Why do you think A is more stable? It's a good question, right? So do you think carbon's going to be very happy with the positive charge on B? No, definitely not. What about A? Do we have any charges? No. So we kind of know, according to cardio rules, molecules are happier if they're less charged, right? All right, that means that A should be a lot more stable than B. So I'll just put A down here. And in fact, because we have time, I'll just go ahead and draw our starting material for A, and then our products over here for B. All right, we know we've got to go over some sort of energetic barrier during this process. Let me actually extend this out. We know that this is going to be our activation energy. And we know that this must be our transition state. So my question for you is, this transition state, do you think it's going to be more similar to our products or our starting materials? Products, right? It's going to be more similar to our products. Why? Because it's closer in energy, right? So our transition state's likely going to resemble this more than our starting material. So let's try to make sense of what this transition state might look like. All right, so in the transition state, we said that's the state in which bonds are being made or broken. We know we're breaking that bond between carbon and iodine, so I'll show that as a dash bond. And then we show this in brackets too with the double dagger on the outside to indicate this is a transition state. It's not something we can bottle up. All right, I'm missing something though. Is the iodine truly neutral in the transition state? So this iodine right here isn't quite neutral. Is it fully negative like on the product side? No, it's kind of somewhere in between. So what we could do is show delta negative, right? To say this is partially negative. Not fully negative yet. It's not all the way detached, but partially detached. Then over here, we could say that this is partial positive on the carbon. All right? So over here, we could say the Hammond postulate tells us the transition state will resemble the products. Does that make sense? So in this case, the transition state has a large amount of partial positive character on that carbon because of that bond being broken. Make sense? I know a lot of this is kind of scary and new for some of you, and other people have seen it like 10 times already in their Gen Chem courses. It depends on who you took Gen Chem with. All right, so tomorrow what we're going to do is we're going to kind of switch gears and get into electron pushing arrows. Please try to get started on your skill builders. Don't put them off until this weekend. Try to start working through them as the week goes on as well.